Welcome to your first Honors Biology vodcast. Today's topic is going to be the nature of matter, and it is our first topic in our new chapter, Chapter 2. And you may be asking yourself, why are we studying matter? Matter is physical science, and biology is life science. And the reason is that to understand all of the chemical reactions that we're going to be talking about in the future in our class, we have to have kind of a general understanding of chemistry and how those chemical reactions are taking place on that chemical level in our bodies. So, Chapter 2 talks about matter, it talks about chemical bonds, and it talks about how chemical bonds form, why they do what they do, the types, and then talks about water, which makes up the majority of our body. So let's go ahead and get started today with matter. So hopefully these words look familiar to you. You've probably seen some of them in the past. And let's start with matter. So matter is anything that has mass and takes up space or has volume. And so basically matter makes up our world. Everything that's on our planet gets put together into some kind of matter, whether it be a chair or whether it be your cat or your dog. All of those things are matter. And matter's basic building block is the atom. And atoms, we're going to talk about in a second in terms of their principles and their properties, but they're our basic building block. They get arranged into varying forms and into various bonds to form our matter. And when we talk about matter, we basically have two types of matter. We have pure matter and we have what are called mixtures. And when I say pure matter, I mean things that are made up of only one kind of atom, and those are our elements. And I'm sure you guys know that big periodic table of elements. But some of the examples of elements that can be found on that table are gold, which is our chemical symbol of Au. We have helium. We have carbon, which is helping to build that pencil that you're probably writing with. So all of those things are examples of elements. And we can even go a step further in looking at all the myriad elements on our periodic table. When we look at the periodic table, we see a broad range of things that we encounter on a daily basis, from hydrogen to oxygen to iron to sulfur to Na, which is sodium, being put together with Cl, which would be our chlorine. So all of those things are examples of elements, things that are made up of one kind of atom, and that get arranged together to form all of our different matter. So in terms of biology, in terms of life, we have a big four, and the big four are carbon, so that's the first one, and we are considered carbon-based life forms, and that is why, is that carbon makes up a big portion of our, let me go ahead and change that, and let me write that in red so that you can see it better. So we have carbon, which gets the abbreviation C. We have nitrogen, which gets the abbreviation N. We have oxygen, which gets the abbreviation O on our periodic table, and then we have hydrogen. So those are the big four that get combined, and we find in the highest percentages, 96 to be exact, in living things. And then we have a smaller four that make up the remaining 4% of living organisms, and that is phosphorus, calcium, and calcium is really important in human bodies for muscles to fire, sulfur, and potassium. And we'll be talking about potassium a lot more when we talk about different ions. So our big four, which we call or abbreviate cone, and then we have our smaller four, potassium, sulfur, calcium, and potassium. All right, so let's talk about the structure of atoms next. So this is an atom. Let's talk about its parts, and let's label the parts so that we can understand where everything is. So in the center here, we have what's called the nucleus of an atom. And you might have heard that word in terms of cells, and it just means centralized. And so nucleus is the centralized part of an atom. And in our nucleus we have protons, and protons are positively charged particles, and we have neutrons. And neutrons are neutral, and they do not have any sort of chemical charge. So here we would have our protons, the plus sign, and here we would have our neutrons indicated with no chemical plus or minus. And then around the nucleus, in these areas here depicted by lines, we have what are called our electrons. And electrons are negatively charged particles. And electrons are very small. They don't have much mass compared to protons and neutrons. And they move very quickly around the outside of atoms. And so we usually depict them in these orbitals or energy levels. And so you need to know for your first quiz the parts of the atom. So you need to know the nucleus, you need to know protons, you need to know neutrons, and you need to know electrons, and any charge associated with each of those. And when we talk about atoms, we see atoms shown in lots of different forms beside the one that I just showed you. So sometimes we see, again, those orbitals depicted by lines like this. Sometimes we just see kind of what's called a cloud model, where we show electrons in terms of an energy cloud. And then sometimes we have the orbitals depicted as different kinds of orbitals for atoms. But all of those are basically models of atoms. So when we talk about atoms, we said that electrons are found in different orbitals or energy shells, and electrons get filled into those shells in different ways. So first we have what's called the first orbital or energy level, and the first orbital can hold a maximum of 2 electrons. And it can hold less. You can have atoms that have 1 electron, like hydrogen, but the most that it can hold is 2. And then we have our second orbital or energy level, and that holds a maximum of 8. Can it hold less? Yes, but it can hold no more than 8. And then our last or third orbital for biology also holds a maximum of 8 electrons. And it can hold less, but it can hold no more than 8. And so we fill them in the order that we just went through them. So if you're trying to draw an electron that has an atom that has 6 electrons, you would first fill in the 2 that go into the first orbital, and then you would fill the remaining 4 into the second orbital for your total of 6. So 6 electrons total, 2 in the first, 4 in the second, is how you would fill that in. So in terms of filling in those orbital levels, we have what's called the octet rule in biology. And the octet rule says that atoms will gain or lose electrons so that they have a full valence shell. So let's write that down. Atoms will gain or lose electrons to have a full valence shell. And what do I mean by valence shell? Well, a valence shell is the last orbital or shell filled. And so any electrons that are found in that last orbital or shell are called the valence electrons. So they're the electrons in the outermost shell. And so these electrons here, 1, 2, 3, 4, 5, 6, 7, 8, are going to be the valence electrons for this particular atom. And when atoms have less than 8 electrons in their outermost shell, they're not full and they're not happy. And when they're not full and they're not happy, they're looking to find more electrons to fill to get to 8 in that outermost shell, or they're looking to lose electrons. So they lose this outermost shell, and then the shell below it becomes the valence shell. And really, because of that, knowing what you know about atoms and knowing what you know about valence electrons in particular, what's going to happen to these two atoms? So here, this atom has 2 electrons in its first shell, and it has 1, 2, 3, 4, 5, 6, 7, 8 in its second shell. But then look, it doesn't have 8 in its third shell. It has 1, 2, 3, 4, 5, 6. So in order for this atom to be chemically stable and to be happy, this particular atom is going to either need to lose those 6 electrons, or it's going to need to gain 2. And atoms are going to do whatever is easier. And so for this particular atom, it's going to be harder to lose 6 than it is to gain 2. So this electron is going to be looking for a partnership where it's going to gain 2 electrons. Whereas this particular atom only has 2 electrons in its valence shell. So this particular atom is going to be looking to get rid of these 2 electrons to a different atom so that the valence shell becomes this second one, which, look, is full. 1, 2, 3, 4, 5, 6, 7, 8. So the fact that these electrons will gain or lose atoms is very important, because that is what makes basically chemical bonds. And chemical bonds have everything to do, everything to do with gaining and losing electrons. So chemical reactivity depends on valence electrons. So the whole reason that we form bonds is because atoms like to be chemically stable. They want to have a full valence shell. They want to have a full 8 in their valence shell so that they fulfill that octet rule. And when we have substances that have 2 atoms that are joined, we call those things compounds. So down here, if we look, this particular atom had 1 electron in its valence shell, and 1 electron is a lonely electron. And so these electrons like to have 2 in their first shell. Remember, the first valence shell holds a maximum of 2. So this particular atom is going to be looking for another electron so that it will be full. And the way it manages to obtain that is by sharing an electron from an adjacent atom. For example, this would be hydrogen, because hydrogen only has 1 electron. And so those 2 hydrogens will spend some time around this hydrogen and then some time around this hydrogen, basically in effect giving both atoms a full valence shell at some point in time. So completing that first valence shell to have 2 electrons. So chemical reactivity, again, depends all on valence shells. So now that we know what causes chemical bonds, and we know that what causes chemical bonds is electrons, let's talk about the types of bonds. So in terms of biology, we have a couple. We have some weak bonds, which are the hydrogen bond and the ionic bond. And then in biology, we have a very strong bond, which would be covalent. So covalent would be the strongest. Ionic would be kind of the medium in terms of strength. And in biological systems, hydrogen is the weakest bond. Now, kind of an interesting aside here is that not in biological systems, or not where we have the presence of water, hydrogen bonds can be very strong. But because of water in biological systems, hydrogen bonds end up being the weakest bonds. Okay, so let's go through each one of these and talk about them individually. So let's talk about covalent bonds first. So covalent bonds are where electrons are being shared. And you can think about this in terms of that prefix co. So co means to share. So we can think about like co-pilots. So co-pilots share the flying of the plane. So co is to share. So two electrons are being shared so that each atom has a full valence shell or outermost shell. Some examples of covalent bonds are hydrogen gas, which we just looked at. So hydrogen has one electron, and if it was just by itself, that one electron is not filling that first shell. The first shell needs two. But when these two atoms bond and they both have one electron, and those two electrons spend some time around the first atom and some time around the second one, it basically in effect gives both of those atoms a full valence shell. Another great example of a covalent bond besides hydrogen gas would be water. And when I say water, I mean the bonds within a water molecule. So oxygen has 1, 2, 3, 4, 5, 6 electrons in its outermost shell. And it needs to have 2 more electrons to be happy, to be chemically stable. And so basically by bonding with a hydrogen that provides 1 electron here and another hydrogen that provides another electron here, we in effect get 8 electrons in that valence shell. Those 8 electrons spend some time around the oxygen, and then those 2 electrons spend some time around the hydrogen and some time around the other hydrogen. So 8 total electrons for oxygen with the addition of the shared electrons from the hydrogen atoms. Next up, we are going to talk about a special kind of covalent bond, and that's called a polar covalent bond. So polar covalent bonds are covalent bonds that are sharing electrons, just like covalent bonds do, but here we have an addition here. We have this word polar, and the reason that this bond is a little different is that the electrons are being shared unequally. So unequal sharing. We're not playing nicely. And a great example of a polar covalent bond is water. So we talked just a second ago about how water is covalent. The oxygen is sharing the electrons from the hydrogen atoms. But what happens is oxygen is bigger, and oxygen is what's called electronegative, and that means that he really likes being negative. He really likes to hog the electrons, and so what happens is those 2 electrons from the hydrogen atoms end up spending way more time around the oxygen than they do around their hydrogens that they originally came from. And what happens when oxygen hogs those electrons and holds on to them for more of the time is that he becomes slightly negative because he's holding on to a negative particle for longer, and the hydrogen atoms become slightly positive, both of them, because they are losing that negative particle for a longer amount of time. So that gives this molecule, this water molecule, poles. It makes the oxygen end of the water molecule negative, and it makes the hydrogen end of the water molecule positive. So we get these 2 different poles on our molecule. And because of those poles, water has a ton of really interesting properties, which we're going to talk about next time. And it all comes back to this idea of polar covalent bonds, or not sharing electrons equally. So remember that when we talk about water. Next up, we have ionic bonds, and ionic bonds are where we are gaining or losing an electron. Gaining or losing electrons. And remember, we talked about atoms are going to do whatever comes easier. So, for example, when we look at sodium here, sodium has a full first shell. It's got 2 in its first shell, and it's got a full second shell. It's got 8 in its second shell. But then look at its third shell. It has 1 lonely electron. Chlorine, on the other hand, has a full first shell, has a full second shell, and it has almost a full third shell. It's only missing 1 electron. So this is a great likely candidate for bonding, because if sodium gave away its 1 electron to chlorine, then it would have a full second valence shell, and chlorine would have a full third valence shell. So that's what's happening here. And when sodium loses that electron, it becomes positive because now it has an unequal balance of its protons in the middle and its electrons. Chlorine, on the other hand, because it's gaining a negative particle and it now has one more negative particle than positive, becomes negative. And so these two atoms are held together now because of those charges that were created by the gaining or the loss of electrons. And so this is table salt, NaCl. And the reason that table salt stays together is opposites attracting, is the fact that when we lose an electron and an atom subsequently gains that electron, that creates charges, and positives and negatives attract. All right, and the last type of bond is a hydrogen bond, and a hydrogen bond is a weak attraction, so it's very weak, between polar molecules. So a great example of this would be between water molecules. So not in the water molecule itself, but between two water molecules, we have this weak attraction. So remember how I told you that a polar covalent bond is what's keeping this oxygen together with these two hydrogens to make our Mickey Mouse. But when that happens and the electrons in there are being shared unequally, we start to see a negative pole on the oxygen end and a positive pole on the hydrogen. So when we have two water molecules lining up in just the right way, it means that one side of the molecule, the positive side of the hydrogen, can be pointing at the negative side of the oxygen. And just like in ionic bonds, when we have a negative and we have a positive close to one another, we have opposites attracting. We have that negative and positive start to pull on one another. And that's what holds two water molecules together. And this property, which has everything to do with a polar covalent bond, is what is a hydrogen bond. And hydrogen bonds are basically why water can stick to itself and stick to other things. So hydrogen bonds are really important in terms of biology. So when you're doing your study guide and when you're studying for your quiz, what do you need to know? So you need to know the parts of the atom and you need to be able to label it. You should understand about the octet rule, that atoms will gain or lose electrons to have a full valence shell. And for most of our atoms, that's going to be our second or third shell, which has 8 electrons. And then you should know the different types of bonds. You should know the hydrogen bond, the ionic bond, and the covalent bond. And you should be able to give an example of each type of bond. So, good luck studying for your quiz. I'm available for help during lunch or after school tomorrow, and let me know if you have any questions by email. Thanks a lot.